water is one of our most important resources, and stream flow represents how it interacts with our environment. And it's an especially important process from an ecological perspective in supporting our local wildlife and vegetation. But it's also important from a hydrological standpoint in understanding how it dictates the health of a watershed. All right, so we looked specifically at the San Pedro River, which is the longest free-flowing river here in the Southwest. It's still a very legally contentious water resource because while it is a critical riparian corridor ecologically, it's also subject to land use pressures. There's a lot of need for groundwater pumping in the area from local communities, which might put stream flow at risk. And so the San Pedro River National Conservation Area, which we call SPRNCA, was established in 1998 to help combat this, and their water rights were established as well, which continue to be disputed over, and also just the stream flow dynamics in this region just don't remain very misunderstood. And so stream intermittency essentially is the variability in stream flow. So it's a diagnostic indicator of watershed health, and it can be used to evaluate whether the water rights of SPRNCA are being met, and also the sensitivity to the flow regime from surrounding ecological and climatological variables. So an important question for us to ask is whether the San Pedro River is getting drier. And so we deployed 14 cameras along this stream to classify flow as either dry, wet, or flowing. 8 of these cameras have 20 years of data. And so those 8 are along this map here, and how dark the dot is essentially represents how much flow it's had over its entire time series. And this is what it would look like for us to install those. And so looking at the overall trend of the flow persistence, annually since 2006, it has been declining. And we see that this pattern is happening mostly in the monsoon season, as we can see mostly in the orange and red, which represent the upstream cameras. And then also right here, the yellow represents some of our drier times of the year, and that is mostly in December. And then here we can see across the entire time series since our cameras started collecting data, we're experiencing drier and drier seasons. All right, so we wanted to evaluate when surface water presence started declining. And so we use this method called change point detection. It essentially identifies the breakpoint in the time series when a statistical property changes. So I did that for mean, variance, and also linear regression structure. And so here for flow persistence, we see a change in linear regression structure around 2018. And we can see the same thing for variance. The most recent change was, again, in 2018. And so we want to know what influences stream flow in this way. And so this method is called convergent cross-mapping. It's a nonlinear dynamical systems method. It's essentially a measure of causal influence. It's a measure from 0 to 1, with 1 meaning a stronger causal influence. However, what we're mostly looking at is the direction of the relationship. And so here, this is for precipitation. And this higher dark blue bar essentially represents that precipitation is driving changes in flow persistence, but we don't necessarily expect that to happen in the other direction. How much stream flow should really tell us how much it's been raining. And so we can actually see that here with temperature and vapor pressure deficit as well. Vapor pressure deficit being almost like a lack of humidity or how thirsty the air is. And these have more of that stronger causal influence. And so I again ran this change point detection with these 2 variables particularly. Here, this one is vapor pressure deficit. I see a change in variance here in 2018, and then again for precipitation, and most recently in 2013. And so what this tells us is that the effect of precipitation essentially has a lagged effect, especially during the monsoon season. And then vapor pressure deficit has that monsoonal effect in the same year for that time And so we've seen a net decrease in surface water presence since 2005, with the strongest being in the monsoon season. When we see a higher vapor pressure deficit, what that corresponds to is dropping flow persistence. And then we see the reverse relationship with precipitation, which has that lag effect on persistence. And so this is really important from a conservation standpoint, because what we've hypothesized is perhaps some of these higher vapor pressure deficits, higher temperatures may be associated with a higher evaporative demand. And so some of our plants may be absorbing more of that water during this monsoon season. And so that's what we're going to be looking into. Sure. Thank you.